Student and Professor Sunil sir, very good afternoon. Students, we have with us Professor Sunil Bhand, who is, Dean University-wide sponsored research and consultancy professor at Department of Chemistry. He did his bachelor and master of physical chemistry from School of Chemistry from Indore, and did PhD in same subject chemistry from Holkar Science College, Indore. And he has research experience of more than I can say more than 20 years now, and he has worked as a visiting scientist and postdoctoral study from Sweden University as well as UK, and he was also a visiting scientist at Indore, and he has teaching experience since 2000, and he started working at the Indore only, and then he joined uh, Pilani Billa Group since 2002, and then he has another administrative experience at BITS Pilani since 2011, 2009, I guess. And he has awarded with many prestigious award and honor, but I'm not going to take much of his time. But Bhand sir is member of IUPAC since 2008, and he is member of International Association of Environmental Analysis Chemistry and many more institutes, I can say. And he is reviewer of various scientific journals such as Biosensor and Bioelectronics Elsevier, and then Journal of Agriculture, Food and Chemistry, and many reputed international and national journal. He has published more than 45 good research articles with high impact factor, and there are I'm sorry for this. And he is also, part of national and international collaboration with different researchers. And yeah, so we are very delighted to have you, sir, and a very warm welcome once again, and on behalf of Srishti. Over to you, sir.
Thank you, ma'am, for your kind words, and good afternoon to all. Uh, I think we would like to, take this opportunity today to, share some of the, opportunities in a emerging area which is called biosensor, and I will try to, take you through a journey rather than talking, about work which is done elsewhere. It will be good to share what we have been doing in this area of biosensor for last now almost 20 years. I have established a biosensor lab at the Department of Chemistry at Goa campus. What you see on the screen is the is the parent campus. As you know, BITS Pilani is an institute of eminence with 4 campuses in Pilani, Rajasthan. Then we have a campus in Dubai, Goa, and Hyderabad. So I have projected the Pilani campus for those who would like to see Pilani campus. And the talk is, as you say, biosensor technology. What are the potential applications? What is the scope in this, area of research? What are the challenges? Of course, equally important to know, and how to convert those challenges into opportunity. So that's my objective today to share with you through this talk. And then I will keep sufficient time for interaction. Those of you who have queries, questions. So that's how we will do. So let me focus on to, yeah. So this is the Goa campus. Just to give a quick glimpse, which Pilani admits MSc and PhD students and also undergraduates through online test. And today we have more than 1,300 PhD students across 4 campuses. So just a quick information for some of the young researchers. And this is the outline of my presentation. Ideally, I will introduce you to the subject. What does it mean, biosensors? What are the various types of biosensors? And then we'll take you in this particular talk today, 2 case studies, focusing on optical and visual detection of pesticide residues and heavy metals. And then if time permits, also we can look at one of the mycotoxin as example. Idea is to share with you, how we look at, challenges around us in the society, and try to see what is available and what needs to be done new and more. and then look at it and try to see where are the opportunities. So that's the focus of the talk. I think acknowledgement is repeated, so you can ignore that for time being. So let me take you first around. One of the areas of what to say research in my lab is the environmental analysis. And as you know, environment connects also invariably to health, because if you're not living in a good environment, take example of Delhi pollution or air pollution. Why Delhi only? It's a global problem in many countries. So if you are not living in a healthy environment, if you are exposed to certain kind of contaminants or pollutants, it will lead to various kind of diseases. So while it is imperative to treat the health disorders or diseases, it is equally important to detect and predict that whether the environment we are living, is it safe, how clean it is. And today we are all talking about clean energy, clean environment, sustainable development goals for sustainability of this earth, and so on. So I'm going to share with you two problem areas within the environmental, domain. That there are various organic chemicals around us because we are growing crops. We are seeing farmers struggling today. You see it at various places in terms of not just policy, but also availability of irrigation, and the water for irrigation, the pesticides. Then you also look at organic pesticide today because we have problems with pesticide uses being harmful chemicals. I'm going to take you through a couple of examples, how this impact us and why it is important to be able to detect any such pollutants or chemicals, not necessarily only pesticide. It is a case study, okay? And similarly, as you see, any of the minerals coming from the earth, it could be natural also, not necessarily anthropogenic or man-made, ideally. So if the mining or minerals are coming into water bodies, today the major challenge is the availability of safe drinking water, right? Free from various contaminants. I'm going to take an example or a case study of heavy metals. Idea is to again share with you what is that we have done. Not only that, what is that some of you could contribute in coming time, maybe in a better way. We don't know. Okay. So that's the idea of this talk, that to introduce you to the subject, take you through the some of the case studies, and try to understand what is it that need to be solved, what are some of our priorities which needs our attention. For example, I have enlisted in the point C here, the groundwater contamination by fluoride. I mean, I have been staying in Pilani campus for initially 2.5 years, and I could see very closely when I was boiling water in my home. That time there were no this ROs. I'm talking almost 18 years ago. Fine. If you boil 1 liter of water, you could easily get, at least 50 to 100 milligram minimum of white fluoride powder onto the, vessel on which you are boiling the water. So you can imagine that if this fluoride gets into, and it is actually getting into the bones, and because of that, there are a lot of, diseases in the population of Rajasthan and such areas which are contaminated by fluoride. I will also share with you another, major problem which country is facing is like the arsenic. And both of them happen to be, interesting enough, they are naturally originated. It's not so much with the human, but yes, there is human, factor. I will come to that, that why fluoride comes into groundwater and why arsenic came into groundwater and what could be the ill effects. And then coming to the point that why their detection is important, why we want to have sensors to detect them, what is its use. And similarly, whenever you are exposed to this will lead to various health issues. And that's why healthcare diagnostics is equally important to have, because we are exposed to the various contaminated food, water, of course, virus today facing challenge with COVID-19. That's very contemporary. So we can't just ignore what is in front of us and talk something which is, relatively, you know, less important. So everything is important for human life. So with that objective, I will take you through some of the challenges which we keep, hearing around us related to this topic. I just tried to, cover some of the media, information for your benefit. As you see in one of the left side, water pollution is killing millions of Indians. I am not sure this number, but it's a media report. But yes, it is killing people. and how we are able to tackle those. As you see, lead, nickel found in blood of people with mystery illness in Andhra. That's very recent report. It's on NDTV. Fine. So many times, what is coming in our food, water, air, we absolutely have no clue, and people start to look around for solutions. So this is one such situation where the contamination of surrounding has tremendous impact on our health and health safety. And similarly, you see business line report, which is quite what you say comprehensive and I would say well supported by the numbers. Because as a scientist, we must believe in the proof, the scientific proof rather than just the news. Okay, so it says 4 crore rural Indians drink metal contaminated water, and that leads to multiple diseases. Fine. And as you see, they say what are the key contaminants reported is arsenic, iron is essential, of course, but then fluoride, as I told you. So arsenic and fluoride is one. Then there are other heavy metals with which people are exposed. Similarly, from nitrate fertilizer, so ammonia, etc. So it is resulting in nitrate as well. So there are various such naturally occurring or human what to say intervened, or because of the our extensive actions on the environment, these have become available in the environment and have found their way into water bodies or even the food, the vegetables. You must have seen recent report. I will probably share in the next slide. So this is one information for us that we can't keep our eyes closed despite working in the labs. It is important we keep an eye on the ground and try to see whether my science can benefit the society. One more, what you see here report, heavy metal toxicity found in vegetables grown in Yamuna floodplain. This was a report last year also by Center for Science and Environment and some other, organizations reported in Economic Times, July 2019. And so that means there is risk in our food also, and there are agencies like Food Safety Standard Authority of India did a nationwide survey, and they try to measure whether it is really true or it is just the report, news report. So there are substantial now evidences which are found through the FSSI report, telling that 9% of vegetables in the country are not edible. I would say not edible means they are not fit for consumption. That means they contain heavy metals in excess of their permissible limit. So there are certain permissible limits and regulatory bodies which do put regulatory permissible limits on the presence of such chemical contaminants. So similarly, if you see arsenic, another major problem which country is facing for a long time. I have been seeing it since 1995 when it was initially detected in West Bengal and Bangladesh. And as of today, it has now spread to Chhattisgarh, to Bihar, and other. It's a purely, naturally occurring arsenic in the geogenic rocks. And because of the changes in the groundwater pH, maybe due to industrial activity, maybe natural, that cause is not established yet. But there was the first report from UK by a British scientist. I think his name was Richard Nixon, by the way. Okay, it was I think 1995. He reported in Nature that arsenic has been extensively found in West Bengal, Bangladesh groundwater. But over the time, you see on the right side, what are the what to say health impacts if people are exposed to groundwater which is contaminated with arsenic or fluoride. But in this particular case, the arsenicosis, as you see, has killed several Indians. That's something which is true. We have several government reports. So the question is, do we have a solution today? Some progress have been made, but then the major question is how to minimize the exposure. Do I have a sensor which is fitted in my hand pump, what you see on the left side, or do I have a sensor in home that before I drink it, I will check it quickly and it will tell me, that this is not fit for the consumption. So today, millions of Indians, that is true, a number which has been, who are exposed to the contaminated arsenic, but we still do not have solution. The only intervention is some filters, low-cost filters, which reduces arsenic to some extent. But we are not able to detect, and the villages, they have no access to such money where they can, afford such filters. So the focus is on the technologies which are for benefit to the society, the weaker sections of the society, down the, the bottom of the pyramid. we need to think around that, and with that objective, at least in our lab, we have been focusing around those aspects, that how we can ensure that the safe drinking water could be, a goal which we can think about how we can tackle those. So I will take some of the examples what we have tried. Likewise, you can also see the report on even fish, contamination of seafood. I belong to Goa, and you see Goa is a coastal state. Most of the local people will eat seafood. It's not just eating; it is their livelihood. They will do fishing and they will do exports. And if this fish and seafood is found contaminated, they suffer economic losses. And today, government is asking, trying to do income of doubling the income of farmers. Fish is also a farming, ideally. So you can see the reports of cadmium 1.03 milligram per kg in fish. That's quite high against the maximum permissible limit, which is 0.05 milligram. So you can see the factor of almost 200 or more. Fine. And these are very dangerous because cadmium can cause cancer. And these are medically established toxicity, or the carcinogenic levels, where you can directly correlate that if it is found in the fish and people are consuming fish, you can understand what could happen to the people who are eating those food. Likewise, from the coal mining or coal particles, this was recently reported in Mandovi River, which is one of the river in Goa, okay, where they found oyster also contaminated with such heavy metals. So the point to share with you is that we need to know what we are trying to probably focus. It has a immediate relevance or long-term relevance related to the environment and human health. Okay, so with that objective, we need to know that do we know what are the permissible limits, and do we have a method to detect them, and then try to decide, okay, whether this water or this vegetable what I am claiming to be contaminated, is it fit for consumption. So as you see, for heavy metal ions, what in the priority list, these are also, by the way, mercury, cadmium, and lead ions are also identified under the Sustainable Development Goals. Fine, and within that, these are identified contaminants worldwide. So their detection is extremely important because they are very harmful. And according to WHO, in drinking water, you see mercury should be, the permissible limit is 0.001 milligram. That means 1 microgram per liter. That means 1 part per billion. Okay, so we need to have methods which can detect them. Likewise, cadmium is 0.003 and lead is relatively higher, which is 0.01, almost about 10-fold higher. And likewise, Bureau of Indian Standards, the European Union. So European Union mercury is more or less same as WHO, and India BIS, but US EPA is relatively relaxed. So idea is to share with you that we need to know the Indian scenario and also the international scenario, that what are the standards set by the world and by us, and we need to first, of course, care about our own health, our own countrymen. But at the same time, many times we may be importing the food, or we may be exporting the material, right? So in that process of trade, you also need sensors. This is an important case study. I will share with you subsequently why the standards are important. And in many cases, I will tell you. Let's look at table below, which is talking about Let me see the laser. Yeah. So if you see this table, regulatory limits in fish and mollusks, okay, or clams and mussels, which are again seafood, and you will be surprised, that while European Union has standards for all three, cadmium, lead, mercury, but US Food and Drug Administration has only for mercury. So what is interesting to note, that while European Union is very much careful about their presence in the seafood, but then US FDA has no standards. Likewise, WHO has no standards. What is interesting for you to know, that it is not somebody who will come and decide. It is who the people who are concerned, and that is where this Food Safety Standards Authority of India has come into picture. It was not there 5 years ago. It's a relatively new agency. The earlier standards were BIS, okay, you were to Bureau of Indian Standard, or before that it used to be called ISI, Indian Standard Institution. But now for the food, this particular agency has been formed, called Food Safety Standards Authority of India. Why I'm emphasizing, if you go 5 years ago, the agency itself was not existing, though BIS existed. but there were no standards for this cadmium, lead, and mercury in the fish or in the mollusk. They have been recently established, and you will be surprised that through a project which we did some 6 years ago through World Bank and the Indian Council of Agriculture Research, we were trying to find out the heavy metal contamination in milk. India is largest producer of milk in the world, and if we can convert this milk into processed milk, that is milk powder, we could earn millions, and that's not happening because. And likewise, fish export, India is second largest, fish producer in the world, and also the export of the fish, which is about 10,000 crore rupees annual production and exports. So if our production is contaminated, they gets rejected. Okay, and from the export, and it's a loss to the farmer and to the country. And not only that, where do you consume it? It will be consumed locally, and our own people get impacted. So the purpose is initially to set the standards. It's not somebody else who will set the standards. So through our project, we forced the government to take a big study and come out. FSI came out with the report and the new standards. It happened just 5 years ago. The fish standards, the heavy metal standards were not available. One of our collaborators from National Dairy Institute was the partner, and he is member of FSSI committee. So we could convince the committee, that there is a need for the new standards and the need for them to be available. And that is why you see today in this table, while US FDA for cadmium and lead in mollusk does not exist, so also by WHO, but at least European Union and India, we have the standards. And that helps to protect our own people's health. So what is the question is, A, we need to know what is good and what is bad. How much is good and how much is bad? What is the tolerance? Do we know the body tolerance of these heavy metals? Do we know what are the diseases which could happen and in what concentration? So that is where we are now trying to come to the main focus, how to detect them. What are the analytical methods? Fine. So conventionally, if you look at, most of you are biotechnology or maybe chemistry students, you would know that we have chromatographic techniques. So using ion chromatography, you can detect various ions, mercury, lead, cadmium, and you can do simultaneously, by the way. Similarly, if you look at pesticide residue analysis, you have the gas chromatography for volatile organic compound. You have liquid chromatography, mass spectrometry for the dissolved residues of pesticides or antibiotic residues, and so on. And they are perfect. They can do very well to a certain limit. Okay, but also believing blindly is not a very good idea. So during our project, which was a funding for $5 million US, idea was to set in the country that what people are claiming is that how true it is. So there were only 5 labs in the country in 2012 which were certified for analysis of water, pesticide residue in water. None of them was certified for milk. So we challenged to the ministry that what is certified is only for water. How do people analyze their milk? Is it safe or not? So they did a survey and we did the survey. And what was surprising, using LCMSMS, out of the 5 labs, none of them could detect in milk, by the way, below the given limits which are set for the pesticide residue, organophosphates. So sometimes you need to prove that what is happening in the system, does it really, how true it is and how good it is. And then accordingly, you set up new facility. So we established India's first milk referral lab through that project in Karnal, which is today operational. Any kind of chemical, biological contaminant you want to analyze, you can go there and get it analyzed. So the point is, you may have conventional method which can do job for you, but they may be taking very long analysis time, as you see in COVID today, for instance, that any RT-PCR test is not less than 3 to 4 hours. And many times that's the only ideal time of analysis, but actual report reaching from sample collection to the report back to the patient, probably at times more than a day, more than 24 hours. Fine. Similarly, they are very expensive. Even today, you see COVID test, which is RT-PCR, not less than 400 rupees. Do you think a farmer or a poor man can afford it? Answer is no. Fine. So the focus should also be on the affordability. The focus should be on how fast and how soon we can detect any target molecule. Okay. Do we really require a lot of trained professional? As you see in case of RT-PCR, I received first call in Goa from the Goa Medical College the moment COVID came, because I have a very high-end RT-PCR in my lab, and they were very keen that can you help us? I said yes, take it if you want. But the point is, then they no, we don't know, we don't have any professional who can operate. So we even train their person, fine, and so on. And subsequently, the government could manage with the large scale testing. But initially, you require trained professional who can run such techniques, fine. More so today, you have seen, except the rapid antigen test, there is no sensor which can go to the field. Likewise, for many of the things, they are not suitable for field measurement. So many times you want to develop devices or sensors or testing technique which could be done on the spot. Fine. So within that perspective, with that context, we are introducing you to the subject of biosensors because of their advantages, which are they are very rapid. Like the analysis time can get down to a few minutes, and in many instances it has been proved, as you will see one or two examples which I will share. Okay. Similarly, they are cost effective, and LCMS-MS is not less than 2 crores, and the sample analysis by LCMS-MS is not less than 2,000 rupees per sample. Okay, and that too, it requires more than 1.5 day for analysis, and likewise for others. Okay. More so, biosensors can be miniaturized. In today's world of nanotechnology, you could see the best example is our mobile phones, right? Which have, and also if you can see the hard drive of the computer, also the pen drive of the memory pen drive, which can accommodate 2 terabytes of data. If you go back 10 years, it was just few megabytes. So miniaturization of the sensors is very important. It is an opportunity. Similarly, you don't need with biosensor very large sample volume. You can do it with few microliters and sometimes with few nanoliters. I have kept one example. Let me see if it is there. So you can do measurements with few microliters or sub nanoliters also, and over and above they can be performed in the field. So with that perspective, let me introduce you to the definition of biosensor and why it is a promising approach. We will discuss that. Okay. So biosensors, as per the IUPAC definition, is a self-contained integrated device, okay, which is capable of providing specific, quantitative as well as semi-quantitative analytical information using biological recognition element. That's the focus. That's why they're called biosensors. There are two components, okay, which is in direct contact with the transducer element, which is your detector. So if you look at this schematic, there are three components, okay. Ideally, you have the bioselective material like enzymes, or you can have antibody, DNA, you can use organelles, you can directly use microorganisms, you can directly use bacterial cells, and so on. And on the other side, you have the various transducer, which could be electrical transducer, and in that case you will use an electrode. You can have pH based transaction, you can have heat based transaction where you will have thermistor as sensor. Similarly, you can do what is a mass change where you will have the piezoelectric device, okay, and for pH change you will have pH electrode, mass change is piezoelectric, and likewise. So you can also have light based transaction. So you will have several kind of signal transduction. Okay. So what you are targeting is you will targeting a target molecule, which could be a pesticide, which could be a heavy metal, which could be a bacteria, which could be a virus, and you have a specific receptor. And the goal in a biosensor is to quantify this target molecule and its interaction with the receptor, and try to see that how they interact. And how do I quantify this interaction in terms of an electrical signal, or in terms of a thermal signal, in terms of a light change, in terms of a mass change, and try to quantify that by way of data processing, so that you are ideally able to not only detect, but you are able to quantify as well. So that's the basic definition about the biosensors. Okay, and a little bit about biorecognition element. Some of you may know very well, but those who are not so much updated, ideally enzymes are very good, what you say, bioreceptors, and they also are kind of a catalyst. So many times enzymes not only have structure, but they also have function, okay, because of the presence of the active site, and many times they do catalyze very specific reaction. So they are highly biospecific. And similarly, due to the presence of the active site, you can use them as biorecognition element in the biosensor. Similarly, there are affinity biosensors, okay, wherein the antibodies, which have very high affinity towards the target molecules because of the complementary regions of structure which detects the target molecule. So you can use antibody in construction of immunosensors, and they are very specific. And as you are seeing in case of COVID, that people are talking about antibody in two terms. One is the neutralizing type antibody, and second is the generation of antibody. So one can also develop sensors based on the antibody detection. Likewise, whole cell biosensors are very easy because you don't need any sample preparation. You can straight away use the whole cell itself, okay, as biosensing element. Other than the naturally occurring receptors like enzymes, antibodies, or whole cell, there are also nowadays, synthetic receptors coming up like aptamers. Okay, it could be synthesized from DNA or it could be synthesized from RNA, and they are upcoming nucleic acid based ligands. They have also very good affinity and selectivity towards the target molecule. So that is another area, emerging area. Similarly, many times you don't want to use the enzyme as a whole as a target molecule. So there is another area where people call synthetic antibodies or synthetic or artificial enzymes. Okay, so molecularly imprinted polymers are nothing but a polymerization technique wherein you try to design your active site structure or mimic the active site structure of your enzyme or mimic the antibody structure and synthesize them. They are called molecularly imprinted polymer. This is the technology which I learned from Sweden 20 years ago. They were the pioneer in this technology of MIPS. So that's very critical. You can make thin films of MIP, unlike enzymes and antibody which aggregate or also agglomerate. MIPS you can make very thin film, like few nanometers, and make artificial receptors. So that's why MIPS are another promising approach in the biosensor technology. Okay, so if you want in general to classify in terms of the transducer, people will say electrochemical biosensors are one of the most pursued biosensor. Reason being its success, okay, and its key secret was the very rapid response time. That electrochemical transaction gives response time in few seconds or sometimes even less. Okay, so that's why its rapidness was the most attractive feature, and its possibility to bring it to the field. I will take an example. Likewise, optical biosensors are another type which are very sensitive. So the advantage with optical biosensor, they are extremely sensitive because of the sensitivity of the fluorescence or chemiluminescence phenomena, wherein you generate the photons. So you can practically detect photon to very low number, and that low number cannot be zero. So the minimum number is 1. So if you want to say I have very sensitive optical biosensor, I will be able to count single photon. Okay, so that's why the photon based measurement for optical biosensor are very attractive. Similarly, there are various, what you say, transducers. So thermal biosensor is another innovative approach, wherein you measure the heat released. As you know, most of the biochemicals within the plants or humans are associated with some way or other some energy, which you call specific heat. Fine. And many times you will see that in the biochemical signal transduction, where the enzymes are catalyzing the substrate, they are associated with some very specific amount of heat. And if you can capture that heat into some kind of electrical energy, you can develop a sensor. I'm going to share one example around that. And similarly, there are resonant biosensor uh, based on the resonance frequency like quartz crystal microbalance. Also, you can have ion sensitive biosensor, as we talked about today, that fluoride and arsenic. Fluoride is F minus, so it's an anion. So we are talking about an anion sensor. Similarly, arsenic is not just present as arsenic; it is either present as arsenite or it is present as arsenate, and in both cases it's an anion, HASO4 minus, for instance. So you are again talking about an ion detection in a biosensing system. So that is where you need to know what are the opportunities, what are the existing transducers. To introduce you to the subject, this is probably the most simplest thing. Most of the people among us will identify this, the glucometer, and that's one reason being the most successful, transducer which has been commercialized. at a very large scale globally. You could see the various, devices by the various companies, at least 5 in this case, are shown to you. And what do you see here is an electrode. Okay, it's called a chip, electrochemical chip, and this is the whole device. This chip is in connection with a transducer. You have an enzyme immobilized here. Okay, and when you put the blood drop, then the blood glucose will react with the given enzyme, and the electron generated are counted through the transducer, and it's converted into the sugar levels, the concentration. That's the fundamental principle. So we are aware of this, and that is why today most of the people are taking this as a platform. That why only blood? I can take uric acid, I can take any other, creatine or any such other parameter and develop this. So this is a very good model to pursue. That if I have a field portable platform, and if I can develop the chip which can, work like the way the blood glucose is being measured, I think it's quite, fast to take it to the market. Similarly, I took the example of visual detection on site. It's a very, what you say, contemporary example from the newspaper or from the news, that wherein you see an antibody test that measures the levels of protein. So it's just an example. It is also used in various other platforms today, particularly the pregnancy kit or many other such now. So these are nowadays another popular platform where you just want to see whether something is present or not, or yes no test. Okay, so to begin with, they are a good example. So similar way you can also make for other such molecules. Since we know this platform, I thought it is easy to visualize. So you can call it as a visual sensor, right? You can do it through a naked eye. But nowadays, with the technology moving fast, you can easily integrate with the camera and quantify also if you really play it well. Okay, so that's the opportunity. So give me a minute. Yeah. So now within that, since we talked about antibody, it is good to know because among the healthcare diagnostics and biosensor field, as I told you, electrochemical and optical are the most promising platform because of their successful commercialization. Okay. Coming to the bioreceptor side, antibody has been the major contributor in the success of all the diagnostics, laboratory-based diagnostics, the pathological tests. Most of the clinical tests are based on the antibody. So if you consider the market potential, it is in billions of dollars. Okay, and that is why the knowledge about raising antibodies, that's one. If we can develop or raise antibodies within the country. Number two, if you have access to very high purity and specific clones like monoclonal antibodies, or you can also have polyclonal antibody. Based on that, you can develop your biosensor. So there is a need for a high quality or high specificity antibody, more so in monoclonal antibody. And within that, you know that they have the regions for binding, and within this region you have the CDR, which is complementarity determining region. This is the light chain, and this is the antigen binding site. That knowledge most of you know. But what I am trying to tell you is as of today, 90% of the antibody market is from abroad. We are only importing. So we may develop our own sensor, but end of the day, you will end up importing, and we need to focus on making India. Fine. So within that, if you have a good antibody, you try to develop your sensor chip, and that's a very good market. So I am focused, my lab is focused around that because we have almost today 15 patents filed, and of which 3 or 4 are granted nationally and internationally. So idea is if you can develop sensor chip. So what is a chip? If you see, for example, you can take a nitrocellulose membrane in case of rapid antigen test or kit, and you couple your receptor on top of that. So your sensor surface is nitrocellulose. But many times, depending on the electrode, you may have inorganic material. You can have gold, you can have silver, you can also have carbon as organic material, right? So you can have a surface on which you will need to couple your receptors, and that's what you want to do. But in between that process, you need some surface chemistry because your electrode surface is not so smooth. Okay, your electrode may be requiring some kind of what to say, normalization of the surface roughness, and accordingly you choose a double-sided tape concept. That means you have a cross linker which will connect on one side to from this to the to the sensor surface, and on the other side you have functional group which could be activated through chemistry, like in case of this you can activate the NH2 group through butyraldehyde activation. Okay, and then through this shift-based reaction you will ideally have your antibody coupled to that. And similarly you can do COH activation via carbamide coupling and then hydroxysuccinimide, and ultimately you get your antibody glued to your sensor surface. So now you have your sensor chip ready. Okay, and now on that chip you can put various target molecules or various ligands, and either do the ligand affinity screening, or you can do molecular interactions, you can quantify the concentrations and so on. So that's the basic concept about an immunosensing platform or antibody based sensing platform. I can do now an optical, I can do an electrochemical, I can do a mass change. In a mass change, what I will do, I will have this mass known. As I add antibody, the mass of this device will change. As I add this ligand on top of it, its mass will further change. And that mass change you can quantify, and that's what you call as mass-based sensing. Okay. So what is that you expect in a good sensor? So you call it performance criteria for a biosensor. So you will expect a good sensor to have high specificity, which is nothing but the ability of a sensor to detect a particular analyte in presence of other analyte. Okay, and that is first requirement, because unless it is specific, there's no point, because you don't know what you are detecting. So specificity for the detection purpose is step one. Okay, once you have that, we just discuss about the various permissible limits. Fine. Now, permissible limit, as in case of mercury, we saw 1 microgram per liter. 1 part per billion is the maximum permissible limit. So suppose a drinking water is containing, let's say, 5 ppb. So you need a minimum sensitivity which can distinguish between 1 ppb and 5 ppb. And that's why you need a higher sensitivity. So sensitivity is, as usually indicate how much of the sensor output changes when the input quantity being measured is changed. Fine. So if I'm not able to distinguish between 1 and 5, then my sensor is not sensitive enough to say that whether this water is fit for consumption, does it qualify above or below. So that is where you need a sensitive system, a sensitive biosensor. Likewise, many times, as you see in case of glucose, blood glucose, there are certain, you need about 80 milligram per deciliter. That's the limit for the blood glucose. So if your sensor cannot measure 80, it can measure only 40, then your sensor is not fit, your dynamic range is not sufficient. So you should be able to go up to 400 or 500 milligram, per deciliter glucose. So you need also, your sensor should meet the dynamic range requirements. Similarly, as you see in case of mercury, if it is 1 ppb is the regulatory limit, my sensor should be able to go 0.5 at least microgram per liter. Reason being, then only I can say that my sensor can detect what is maximum permissible, and then because my limit of detection is lower than that, I am able to distinguish between the two. Okay, so limit of detection is measured by at a very specific confidence level, and it should be minimum 95%. Similarly, you need to have ability to quantify. So while you are able to detect, you should also need a limit of quantitation, and they cannot be same. Usually LOD is lower than LOQ. Fine. So LOQ is the lowest concentration at which a measurement is quantitatively meaningful, and which is normally more than LOD, as I said. Okay. So you want to be able to quantify, not just being able to detect. And subsequently the response time depends on the type of target molecule. If you are looking, for example, a pesticide residue, it can wait maybe a day or so. That's not a big deal. But supposing that you are detecting COVID, as we see today, or if you are wanting to detect, for example, a bacterial infection among the infant, as you know that infant, unless you start the treatment, they will not be improving. And there are many infant mortalities, by the way. So that is why the response time in case of bacterial sensor is one of the important requirement, that how soon you can detect. As you know, the culture, the conventional gold standard culturing technique require at least a day for identifying the bacterial infection. So Biosensor has a good potential. We recently filed 2 patents on a bacterial sensor, ideally where we can now detect an E. coli in less than an hour, okay? And we are trying to make it to a few minutes. So idea is, the question is, in certain instances, you need a very rapid response. If you take, for example, detection of sepsis, infection, another type of infection, okay? And if you see, most of the patients worldwide are dying at the operation table just because there are no rapid sensor to detect infection, how much it is. It's a very burning and challenging opportunity. If you can detect sepsis in a very short time, fine, because there are no good sensor today to detect sepsis in a rapid way. Okay, and likewise, they should be reproducible wherever you perform. And the question for country like India, or economically, what to say, less rich countries, we are still now going from developing to the developed, but our economic GDP still has to match that. So you want reusable sensors because it's not good for environment. So if you consider today the glucometer in India, as you know, India is becoming a hub of diabetes. Almost 15% world diabetes population is residing in India. So this number is rapidly increasing. And if you see glucometer, suppose you use, for example, 15 crore chips every day, and you throw them out in 1 month, how many chips you will create as a waste, as a electronic waste. Fine. Not only the waste, the cost. So you need reusable sensor. If you're able to make a very reliable and reusable sensor, nothing like that. So that is another area that most of the world focuses on the consumption as a market. Okay, but in the interest of the country's economy, it is good to have the reusable sensor, because it's not just economy, it's also environment. Okay, so if you can make reusable sensors, it serves the both purposes. So these are some of the performance criteria for the biosensor. And let me introduce you very quickly to the enzyme thermistor or thermal biosensor. It's a very simple thing, and the human body exactly works like that. If you see most of the biochemical cycles in the body, they are very well connected with this thermal signal transduction. So ideally, what you do is you try to measure the evolution of heat from a given reaction, which is delta H. Okay, so if you take, for example, a biochemical reaction using an enzyme, and let's say glucose oxidase, fine. So glucose is converted into gluconic acid and hydrogen peroxide, and it will be associated with certain heat or energy, which will be either joules per mole or kilojoules per mole, fine. And depending on your concentration of glucose, you will have the proportional amount of heat liberated. So in a thermal biosensor, ideally you measure the specific heat resulting from this kind of a hydrolysis or a specific catalysis from the enzyme. All right. Some of you may have heard something called, what you call it as calorimeters, fine. And some research institute, you call it isothermal, calorimeter, fine. So ideally the calorimeters are nothing but the thermal sensors. But when you put an enzyme in proximity with a thermal transducer, so what I'm trying to convey is, in case of, this is a thermistor, forget this COH group, this is a thermistor. What is a thermistor? A thermistor is nothing but a device which converts heat into electrical signal. Now, what it is made up of? It is made up of metal oxide layer. Okay. So the moment you expose it to a biochemical reaction, it will sense the heat and generate the current. Only in this case of a thermistor, you will have an enzyme here. If you are talking about an enzyme thermistor, so you will have enzyme in close proximity with your transducer, which is thermistor, and as a signal, it will generate the heat to an electrical signal. I will come to that slide soon. So this is one such setup which was developed in Sweden, the group I worked to begin with, and they are the original inventor of this enzyme thermistor globally. I happened to work with the group 20 years ago. This was the original setup which I could bring to India in 19. This was made in 94. It is still working in my lab for last 20 years. I got a gift as a DBT project. It was a DBT and Sweden project jointly. We developed this enzyme thermistor application. The instrument was developed 5 years ago in 1990 or so. but I developed and transferred the technology for cholesterol biosensor as well as the urea biosensor on that. But today this whole instrument has been miniaturized. As of now, you see it is almost 18 inches, and this is almost similarly 18 inches. The printer is gone. Now there is a completely on the mobile phone. These pumps are miniaturized. The whole setup is miniaturized. This whole setup, which is inside, is having a kind of a setup of immobilized enzyme in the cylinder, which is through a flow pump. But this whole system today exists in the form of few centimeter column. You will be surprised. Fine. So this is the potential of nanotechnology, and even this transducer is now into size of few inches, and the whole setup is now into a chip of few inches. All right. So that is the potential. So ideally, a thermal biosensor is converting or measuring this biochemical signal transduction very specifically, and so far at least 45 analytes have been demonstrated using this, and the response time is in few seconds. All right, because you are using a thermistor which is sensitive, you can measure a change in 0.001 degree. Fine. And if that change is recordable, then you are measuring the analyte hydrolysis or interaction very fast. Okay. What is interesting is that when you use immobilized enzyme in a bioreactor, we use the control pore glass. Okay. And control pore glass is nothing but silica which has pores inside. So what you see is the spheres. These are empty spheres. This was invented by Corning in late 80s or 75 to 80. Okay. And these are very specifically made. Corning was holding the patent for it. They made billions of dollars using this technology. Today this material out of market. One particular industry has bought last year, so now this material is not available. Fine. But in principle, you have nano size pores, and in those nano size pores, you put cross linkers like silane layer, you functionalize it, activate the group, NH2 group, and then couple the enzymes. And now you see the red color is nothing but representing an enzyme which has been loaded inside the nanopores. And this whole single particle is like few micrometer, ranges from 1 micrometer to 2.5 micrometer. And within this, these are pores of few nanometer, something like 2 to 5 or 7 nanometer. Fine. So these are created inside a single microparticle, and you use something like maybe 10 milligram of this powder, on which you can load maybe a few hundred units of enzyme. We did the urease in this case, immobilized urease, and then characterized the urea hydrolysis, and it became a urea sensor. And then we subsequently demonstrated in the farms, we demonstrated in the urine, you demonstrated in the milk adulteration. So this was one example to tell you that integrating nanomaterials with biological receptor is a tremendous opportunity, and I'm sure many of you know that, but many of you may still find huge potential, because you can use various biocompatible nanoparticle which can be injected in the body. You can have in situ sensor nowadays. So far there is only one biocompatible material approved by FDA, and that's liposomes. Okay, so you need to develop newer drug delivery platform. That is another opportunity, because many of these biochemical reactions happens within. Okay, so you have that opportunity also to develop that. Coming to the, based on the active site presence in the heavy metals, let me keep track of time. Yeah, we will close at 3:10 or 3:15 and then have discussions for 15 minutes. So based on the active site presence in enzymes, okay, the lock and key mechanism, many of you may be knowing that if you have an active site in an enzyme, the substrate will go and specifically bind to that active site, and then accordingly it will get converted into product. And that is why the enzymes are so specific. What I tried to show in this case is the reaction where the substrate is getting converted into product. And if you see on the right side, I hope you are able to see my laser pointer. On the right side, this microwell plate, one is the white, 1, 2, 3, 4, 5, 6, and other is producing color. So the one which is maximum color is no inhibitor. Okay, and the one which is with reduced color is in presence of the second step, which is the inhibition. So if you put inhibitor, it could be a drug target molecule, it could be a heavy metal, it could be a pesticide, but enzyme has to have that kind of active site. And if it binds, then accordingly your reaction is blocked and there is no more inhibition. So you are going back to the more color. So in absence of inhibitor, you will have the white color. or the less yellow color, and in presence of inhibitor you will have in absence you will have full yellow color. So this we demonstrated on a zirconia particle with a very specific purpose. So this was first ever report of zirconia particle being used, not just sensing, we also did remediation of pesticide. So this was the first report on how to capture the pesticide first, and also same time sense it. So you don't need a separate sensor. Okay, this is very simple mechanism, and we demonstrated with zirconia particles in a 96 well plate format. But today it can be done in a microliter bend of tube. Okay, and likewise your knowledge about active sites of enzyme will play the role. So since many of you may be aspiring for a career in the area of protein engineering or enzyme engineering or neurobiology and so on, the knowledge of active site is the most critical. What I learned, that I still in this 20 years period I could witness only 3 or 4 new active site structures. So that's an area which is of immense interest, wherein the structural biology and the protein crystallography is extremely important. And once you know the active site structure, it is much easier to design your sensors. This is the structure which was predicted by Joel Sussman from Israel. This was around 2002 when I was very closely working on the acetylcholinesterase sensors, because they are neurotransmitters, and based on that you can develop the pesticide sensor. So the knowledge of active site structure, this was reported by the Sussman group that time. Similarly, now coming to the heavy metal part, using nanoparticle and based on the inhibition principle which I shared, we developed in our lab iron oxide nanoparticles. We synthesized ourselves, functionalized them with the silica as the cross-linker, aminopropyl silicates, APTs, triethoxysilane, and through the silane layer, we activated and coupled the alcohol oxidase enzyme. Some of you may be interested. The structure of this enzyme is still not deciphered. I have been talking to various groups worldwide in Germany or in US or UK. Even one group in IIT Guwahati which tried a lot on this enzyme, they could not succeed. So this alcohol oxidase enzyme, which is very specific to methanol and ethanol as substrate, the structure is not known. However, it is very sensitive to certain things. So in 2012, we reported for first time without any nanoparticle that if you put mercury and alcohol oxidase together, we could detect 1 part per trillion of mercury, which was best ever detection limit in the world. And so far it holds. That world record is standing. Fine. So the question is, what you try to do is, if you know that the inhibition is occurring very specifically, and if you are able to quantify. So what we did, we coupled the alcohol oxidase on this silica nanoparticle through silane layer, put them in 96 microwell plate, put methanol substrate and HRP enzyme, and put a chromogen like OPD, which generates a yellow color as you see here in the right side, the upper part. Fine. So yellow color when there is no metal. So you can measure either visually or you can measure at 450 nanometer. And when there is mercury, the color will fade up. So it will go close to the transparency. And that is where your transducer comes in. That how sensitive is your transducer will dictate the detection limit. All right. So the integration to nanomaterial helped us, go from 1 part per trillion to 0.05 part per trillion. So this work was published, I think last year in December from our lab with using nanoparticle. But in 2012, we reported in the free enzyme assay with 1 part per trillion. There were people who were not believing. Then we had to share with them the original results, etc. So the results are reproducible. Fine. So this is one such way where you can make not only visual, but you can also make the measurements. So how you use it, you can use a plate reader, for instance, and measure the absorbance. You could see here the real absorbance values are shown 0.53, 0.59, and likewise, so 0.099, right? So this is how you measure your absorbance, and this is a visual. So sometimes your naked eye may not be able to distinguish well, okay, the color in the well, and that's why you need a machine readability. And that is why today's world, people are now talking about having such detector in a mobile camera or a mobile phone integrated camera. There are now various reports So you can actually measure this thing through in the field through a mobile phone. And we did with a normal, mobile camera, a normal smartphone. Even you can quantify with that. It is sufficient enough to develop a simple low-cost sensor. So you don't need this sensitive equipment which cost around 6-7 lakh rupees. But nowadays with the miniaturized technology, you can do with your own good quality phone, and that's very much doable. Okay. So what I talked about is the colorimetric sensor using the visual detection plus the machine-based detection. Okay. And likewise, as you see here, we went down to 0.005 nanogram per ml of mercury 2. This was the world record in detection of mercury in drinking water. Okay, what you have the detection limit is 1 microgram per liter, 1 ppb. Okay, but here we are talking of 0.005. Okay, so multiply it by 1,000 will be the liters. Okay, so this is how you try to see the specificity that the cadmium and lead are not detectable below 0.1, but they are also interfering about 2 nanogram per ml. So ideally, the idea is not to go too much into the numbers, but idea is to see how low you can go, how far you can go. That's your dynamic range from 0.005 up to here, let's say 1 or 0.8 nanogram per ml, and you want it to be detected as sensitive as possible. You will be surprised in Goa today, it has the largest number of dialysis units. And one can ask or wonder that why Goa needs so many dialysis units. And the number of dialysis units have almost doubled in last 5 years in the hospital, several new units. What is the reason? So many kidney cases. There is direct correlation between probably such heavy metal contamination in the fish, could be in water, and the numbers of patients are in thousands. One particular village is specifically suffering from the kidney diseases over the decades. So that is one reason we need to identify scientifically what is happening around. Do we know the cause? There are still not confirmed reports, but the number of dialysis units are doubling in every 5 years. Okay. So another quick example is while we talked about optical detection, coming to the electrochemical part, you have seen this pH meter in the lab, you have seen the conductivity electrode in the lab, wherein you have the AgCl electrode and you have the pH sensitive electrode. Fine. So you can detect the pH of the solution, you can detect the conductivity of solution. And why I'm sharing this example, because we talked about ion sensors, right? Fluoride ion and arsenate ions, arsenite ions. So if you have ions, your conductivity of solution will change. And you cannot put such big pH meter, though now Eureka 4 has integrated this pH meter into its RO purifier, by the way. They have launched this model this year only in January. Okay. So ideally now the customer has to pay 35,000 more because they have integrated a pH meter into the system. But that's not enough. Can we not have much cheaper conductivity meter and so on? So likewise, there are now, as you must have seen in the lab, you have these pH censored strips. The problem is they are not sensitive. They cannot separate so easily between the low pH changes. Fine, from 7 to 7.1, you can't have. You can have 7, 8, 7.5. But in drinking water, you usually are around 7, which is neutral pH. So you can still make these strips more, what to say, specific and better resolution in terms of the pH numbers, and that is something not many people are pursuing in the world, but only the Merck and few companies have captured this market, but that too with a relatively less separation. So if you can resolve the color in a better resolving power, you are in the game. Fine. And in that perspective, what we did, you have seen these electrodes which are about 2.5 inch or 4 inch or 5 inches. We made a micro electrode recently. Okay, so with the help of microfabrication technology, work we did in collaboration with IIT Delhi about 7-8 years ago. We got now 2 international patents on this device. It is granted already. And in that, what you do is you make the miniaturized electrode. These are few microns. Okay, and then connect to an electrochemical system. Usually, you see the 2 wires, which are usually conventionally you dip in any electrolytic cell. Remember your school days when you dipped zinc electrode and the carbon electrode. Likewise, you have the patterned electrodes. They are 2-dimensional electrodes. Okay, and then you put your antibody on top of that and then optimize the parameter. Using this sensing platform, we could detect, the aflatoxin to the best detection limit in the world. Again, this is a world record. This is reported by World Mycotoxin Journal, not by us. That this is so far the best detection limit achieved for aflatoxin M1 in milk. We could go down to 50 parts per trillion. Any conventional equipment cannot detect less than 1 ppb. Fine. So even if you go by the HPLC, Cobra cell method, the post-derivatization method, you cannot go less than 2 ppb aflatoxin M1. So we reported first ever time, and using all the standards, we then performed a test where the sample was, sent to Italy, third party, and then we did the blind results and we passed the test. Okay. So this is how you rigorously develop something, don't show in the halfway, and based on this result, we could recommend aflatoxin M1 level through FSSAI in India for milk. So that's the message I want to tell. Sometimes you can drive. It's not you wait for somebody to make a traffic light for you. You have to be the torch bearer and go forward. This was very simple technology using not very high-end nanotechnology, but it was a routine lithography, but it could be done. And similarly, you can integrate nanotechnology on top of that. So on the electrode, we generated some nanostructures. This work was done in collaboration with a Swedish group. Okay. And then we measured the estradiol, 17-beta estradiol. Estradiol and BPA, they are available in the plastic. Microplastic is now a problem. And within the microplastic, estradiol can leach out, and it's an endocrine disruptor. So it is classified now as an emerging contaminant. Okay. So within that, we developed, using the same platform, an estradiol sensor where you could see we went down to 0.1 picogram per ml concentration. So this is where you need to set the standards. Idea is to tell you why we integrated nanostructures, because our goal was to go down from 1 to 0.1, or go down from nanogram per ml to picogram per ml. And that is where the sensitivity comes into the picture. And sensitivity was achieved by way of integrating nanostructures. These are 200 nanometer zinc oxide nanorods grown on a silver wire, a silver microelectrode. Okay. So this is how you try to develop those systems. I think considering the time constraint, I will probably take you through a last slide. This was just an introduction to aflatoxin. So likewise, we took the titanium dioxide as a material, and in this case for aflatoxin A, we collaborated with a French group where we used aptamers as the synthetic receptors for detection of aflatoxin. The message is sometimes you may not have all the expertise, so importance of collaboration is very much there. So in this project, we collaborate with a group which was developing the aflatoxin, but this sensing mechanism was designed by us, wherein when the OTA will bind, to the aptamer, the conformation will change, and as a result in conformation, there is a fluorescent signal. What I am trying to show you here is you need to choose your nanomaterial and nanostructures very carefully. You should be very selective in thinking about why I should use it. Just because TiO2 is reported by others, or why I am going to use TiO2. Is there a purpose for that? Do I want to improve the detection limit? Do I want to reduce the response time? Do I want to make it low cost? Okay, and what is my purpose? So in this case, we were looking at fluorescence turn-on sensor. Okay, and not only that, we developed a miniaturized fluorescent field portable sensor. So there is a portable fluorimeter now. This was designed with a company in France near Paris. Okay, and the design was mine, of course. So we developed a fluorimeter so it could measure the fluorescence in the field. Okay, and the aflatoxin was detected in field. The reason was very simple. French people wanted to measure aflatoxin in wine and beer, and we wanted to measure in milk. Well, the India interest is in milk, okay, or other such crops. So I think with that I will stop. This is for antibiotic. So I should give the credit to all the contributors. So we had a collaboration with BRC Mumbai, wherein we developed a chip for the tuberculosis screening through Swedish Research Council and DBT. We did a lot of work on the Enzyme Thermistor. With UK, we worked on the screen printed electrode. ICMR now we are working on the malaria diagnostics. With Professor Danielson and Willander, We had almost 20 years collaboration. We still have ongoing project. With RRK Indore, we use synchrotron radiation to make the new devices. Dr. Balasubramaniam is with the BRC Mumbai. National Agriculture Science Fund funded most of my projects. Also UGC consortium in Indore, Professor Marti and all my PhD students. So idea is it's a teamwork. I won't take the credit for myself. It's a team spirit. Today the collaboration is very important to take up the challenging work, to solve more complex problem, to make solutions better. I think with that remark, I will close with a thank you note to all of you for being so patient to hear my talk. And any question, we have 15 minutes with us. You are most welcome to ask. I will try to respond in my given capacity. All right. Thank you. So, Dr. Barot, over to you, ma'am.
Yeah, sure, sir. So students, now the floor is open for your queries and discussion. So please go ahead.
Hello, sir.
Yes, please.
Sir, after seeing your this presentation, I thought of one biosensor kit to detect the blood-borne pathogens in their early stage. Like we know there are malarial parasites and some viruses,
Correct.
and also the metastasis of cancer is also flown through the bloods. So can we make injectable nanoparticles which will have a multi-targets, and it will flow through blood reacting with those like example viral particles for few minutes, and then we will have a small miniature oximeter like machine in which we will put the our finger, and when those particles reacted will flow through that region, so they will make some kind of thermal or optical signals. So in at home also we can do those tests just like glucometer. Is it practical or possible?
Chetan, idea is good. Let me tell you. So idea is the first thing in the world, which I learned. Okay, that unless you have idea, you cannot pursue it. So idea is in place, right? Now there are some groups which are working. Now only difficulty or different, or you have to be methodical. You cannot suddenly go to the human trials or testing. You need to go step by step. Start with your laboratory experiments and try to see develop a transducer. Once you are able to see through, then you take it to the animal studies. You can't suddenly go to human trials, right? And the moment you talk about human trials or animal trials, you will have regulatory aspect. Bear those in mind, and that's where you need collaboration. Got it? So if
Yes,
you
sir.
have facility to work in the lab, your own lab is very good. But if your institute does not have those facilities, go and collaborate. There are very many organizations. So idea is worth trying. Got it? There are some reports which I encountered within the group I collaborated. They were probably the first to do a underskin measurement, underflow condition, creatine sensor. Okay, and that is how I saw in one such case. But yes, the answer is yes. We should try. We may fail, but we should give a try. We may succeed also. Chances of success, you need three factors: a sensitive transducer; B, a delivery system which is non-toxic. Fine, because that is where the whole risk is. Fine. So if you can use the existing platform, like I told, the biocompatible material, uh, it can be tried with that also. I remember one such big company, Roche, was trying 15 years ago an underskin sensor. Okay, but they developed the toxicity. They injected some material below the skin, but unfortunately, it developed the toxicity. So the whole game was: do you have access to a good biocompatible material, which will not be toxic? Got it, Chaitanya? That's my
Yes,
my
sir.
views. Okay,
Thank you, sir.
but idea is very good. Keep it up. And you can think about a non-injectable also. Why not to begin with? Think about a simple kit which could be in the labs, right? Anybody else?
Hello, sir. I am Sunil from Maharashtra, sir.
Swapnil, go ahead.
Sir, is there any biosensors in air pollution field or air pollution analysis as well?
There are biosensor, yes. I did not cover here, but I can tell you what are those type of. You remember I used a word called resonant sensors. Okay. So let me go back. One of the 4 types of sensor, I did mention about the resonant sensor, but then I did not cover it due to brevity of time. So in resonant sensor, if you search Google search, it will called quartz crystal microbalances. Okay, Swapnil. So if you Google it, quartz crystal microbalance, what you have in there is a quartz crystal, all right, which is coated with glass. Sorry, coated with gold. So quartz crystals are coated with gold, and on that gold, you will now use this chemistry what you have seen here. Are you able to see my slide?
Yes, sir. Yes, sir.
So here you assume now that this brick red color surface is your gold, and these lines which are representing is the quartz. Why quartz? Because quartz resonates at a given frequency. Okay, all right. So when you will resonate this quartz crystal at a given frequency, it will show you a corresponding mass of the antibody which is coated now onto your gold surface. Okay, so we are talking about now a quartz crystal resonator. All right, so under the influence of a given frequency, which is usually 50 hertz or like that, but you have different frequencies for different crystal, you functionalize your this with an antibody. Conventionally, if you see for air pollution, quartz crystal were the first such sensor, not biosensor, by the way. Quartz crystal were the first such reported sensor which are commercially used under a stack monitoring kit. All right, so you expose these tiny quartz crystals to the air and capture the air particulates on that and see the change in mass. And they were also among the first to be used on the for measuring the volatile organic compound, particularly the benzoate, pyrene, and all that in the air. All right, from the air pollution. Fine, even if you want to distinguish between diesel and petrol and this. So, but then if you functionalize with an antibody, you can measure the particulates also of interest in the air. So, you got the point what I'm saying?
Yes, sir. Got it, sir.
They are called QCM, quartz crystal microbalances. They are little expensive, but they are today the gold standard. All right.
Okay, sir. Sir, no matter, sir. I will study detail about that and make a report and mail it to us.
Most welcome, Swapnil. I will be happy to help you. Not a
Sir,
problem.
thank you very much.
I have a QCM unit in my lab, by the way. It's a very sensitive one. It's not only microbalance, it can go down to nanograms. It's called a nanobalance nowadays. It depends on the ability to measure the lowest amount of mass. So NASA did this experiment 6 years ago. So what they did, they sent these chips in the space, and while re-entry, they threw these chips in the environment, and then they collected it, and then they were nothing but the quartz crystals. Fine, and then they collected it and saw what is that they could measure. So it's a very popular technique. So advantage with quartz crystal is you can throw them or expose it to air. It will not have any problem. Fine. Only they are little delicate. Okay. Anybody else has? Feel free to ask.
Hello, sir. Good afternoon, sir.
Good afternoon.
Actually, sir, I'm not a background of the biotechnology. Actually, my background is a pharmaceutical science. So,
Okay.
sir, I think enzyme-based, sir, biosensor can be applied in the pharmaceutical industry, sir.
Very much. It is used very heavily. Rather, if you look at, there's a large number of companies which use enzyme to screen the basically what you are looking at. Suppose if you take Alzheimer or such diseases, in Alzheimer, what people are looking at the aggregation of a certain protein, right? But similarly, there are many cases where you look at the active site wherein an enzyme is there, and ideally you design the drug. So it's very much possible, Mr. Devraj, to answer in short, yes. Taking the second example, I tell you, have you heard of biosimilars in pharmacy?
Yes, sir. Sorry, sir. Can you?
Have you heard the word called biosimilar?
Yes, yes, sir.
They are screened based on the antibody. So whole screening of biosimilar is done using the biosensor today. The affinity characterization is done using a biosensor.
Yes, yes, sir.
I am in Goa. There are 400 pharma companies registered, all big and small.
Oh,
Name
okay,
it from
sir.
Sanofi to Pfizer, and they keep approaching us many times to measure the KD values.
Yes, yes, sir.
I hope you got my point. So enzymes, yes. Answer to your question is yes, and that's a very key area.
Yes,
Very
yes,
key
sir.
area. Okay.
Yes, yes, sir. Okay, sir. And sir, also it is applied, sir, in the hospital, sir, for the emergency control, sir, for purpose, sir. Emergency control, I mean, sir, patient treatment for cancer treatment, and their
Antibodies.
anti-cancer treatment, sir. So also this.
Antibodies, yes. Antibodies, yes, because that's why the biosimilar drugs are developed. Idea
Yes,
was why biosimilar, because for HIV, people wanted to make the cost of treatment to $1 per day, if you remember. Got it? Currently, it is $50 per day, the cost of treatment, either HIV or cancer using the humanized antibodies. Okay?
yes,
And
sir.
that is why the whole purpose is if you can do production in India, the cost will come down
Yes, yes, sir.
for the patient per cycle, per day treatment cost. The target by WHO is $1 per day, but the current cost is $50 per day.
Oh, yes, sir. Okay, sir. Thank you.
Thank you. Anyone else?
Any more questions? Not only this topic, you can ask anything in field of biotechnology. I think sir would be happy to answer that.
Yeah, if I know the something, yes. In my capacity, yes.
Of
Of
course.
course. Not a question. You can ask if you have any query. I can connect you to others if need be. Not a problem.
So sir, they are undergraduate students, and
Understood.
they
Right.
have not even started a small projects at colleges.
Right. Yeah.
That is the reason they are just learning stage.
I think that's fine. I think learning is the first step, so they should not be shy away from
Right.
learning. I am also learning still, so I think absolutely fine. We keep learning.
Yeah.
Sure, ma'am. Yeah.
Okay, so students, I guess there are no more questions, but if you have any, I will send the email ID of professor. So you can contact him with the proper query and proposal of your idea, so he can guide you the way he can.
Yeah,
And
I will be happy. Sure, definitely.
yes, sir.
Yeah.
So we are ending here the session, and thank you so much, sir, for your time and for your support and
Oh,
contributions.
thanks so much. Yeah, it was
Also,
nice.
you have accepted our invitation, and this time in your odds conditions. Also,
Great.
you have managed this,
No
so I'm
problem.
really grateful,
Yeah,
and it's
sure.
wonderful session. Thank you.
Yeah. Thank you.